Hello, this is Jonathan Templin, and this lecture is an introduction to how we assess model fit in multivariate models. That assessment of model fit is with respect to the data absolutely. So this is kind of an absolute version of model fit. This is a lecture for our EPSY 905 Fundamentals of Multivariate Modeling. So in this lecture, we'll talk about model fit and how to look at it to see if a multivariate model fits the data in an absolute sense. If you'll recall from our introduction lecture, the issue of model fit is somewhat novel to multivariate models, particularly when compared with univariate models, in that in multivariate models, the model fit has to be checked before looking at your results. The key is that the multivariate model can quickly not resemble the data that you have, and then when it does that, the validity of the results gets called into question. So what we will do for this lecture is to pick up, we will be picking up where we left off in the introduction lecture. We're going to use the same data set. This is a simulated data set I created based on a study from 1994 involving self-concept beliefs and self-efficacy in mathematical problem solving. The study had 350 students involved. There was some missing data. And again, the results from this may or may not look like the results listed in the paper, and that's because of the characteristics of how I simulated the data. So here are the variables. We have the sex variable. We have a bunch of scales involving self-efficacy and other versions of math. The two that we're going to look at today in this lecture are the perceived usefulness of mathematics with the reliability of 0.93 and mathematics performance, sort of the performance on an 18-item multiple choice math test. Now you'll note reliabilities for these are not 1, and so we're already violating one of the assumptions of our model, but to remedy that is beyond the scope of what we can do in this class. So we're going to get back to methods of examining model fit. So we are picking up where we left off in the introductory lecture on multivariate models. We're going to start with the last model we had there. That was the model where we were modeling performance and usefulness both as empty models, but we set the covariance between the two equal to 0. If you go over to the R syntax for this lecture, you can read in the data and get everything loaded. And when you get down to the bottom here, you'll be able to find the model 3 here with the Lavon syntax. And so we're going to take model 3, we're going to submit it to Lavon to be run, and then we're going to look at the summary. And from here, we're going to describe all these numbers up top, what they mean, and how we can interpret model fit based on them. So just to remind yourself of the model, again, performance and usefulness are the two dependent variables. Each of those is modeled with the intercept, which will become the mean of the variables in the analysis itself. It also has an error term, and the covariance matrix, or the residual covariance matrix for this model, ends up having the sigma squared error for both performance and usefulness down the diagonal. And the off diagonal is a value of 0, where the covariance is not estimated. So here again is the syntax and the results. We saw the means 13.966 for performance, 52.5 for usefulness. Variances 8.75 for performance, 249.201 for usefulness. And we also looked at this graph where we kind of superimposed contours of a multivariate normal over a scatter plot of our data. And there's no easy way to determine whether this is good fit or not. So we are going to go and involve model fit statistics, or talk about model fit statistics to put more of a quantitative analysis to whether or not a model fits the data. So again, model fit is really the utmost concern when you fit a multivariate model. If your model doesn't fit the data, then you're likely to have some type of estimates that may not mirror reality. And so therefore, not fitting the data is a first step when evaluating your model itself. Looking at model fit is a first step of looking at the model itself to see if you can even interpret the parameters. So that being said, you'll note that there are cases I've encountered in life where people will find they have absolutely fabulous, great model fit, but then they look at the results, and the results themselves are just not helpful. Maybe they have zero effects that are significant. And it turns out model fit, again, is a kind of a necessary precursor to even looking at or interpreting the results of the data. To have something worth reporting, not only do you have good model fit, you also have to have results that you can interpret and describe further. So model fit's the first step. We're going to begin this discussion with what we call global measures of model fit. These are overall number summaries of how the model fits the data across all the dependent variables in the analysis itself. After we get done with global model fit, we'll move into something we'll call more localized or local model fit, which talks about where the model is misfitting in particular places with respect to more specific variables rather than just the entire set of them. So, global model fit information, where whenever we have models that are, we have outcomes that are conditionally multivariate normal, like we have in this example, there are numerous types of global model fit information. But generally speaking, each number that we see tries to assess how well the covariance matrix implied by the model compares with the covariance matrix that we have in our data. That's why what I mean by that is effectively that all of the possible models that we could come up with for a multivariate model have a covariance matrix that's nested within the one where we have a saturated version of it. Right, so we estimate all of the parameters in the covariance matrix. So most of the model fit statistics are going to come from comparing the analysis of our model right here with the saturated model, one that we may not even run, but in background behind the scenes, Levon is actually running this alongside of our model. So we're actually going to start doing model comparisons with the overall kind of answer key for what the best model had happened to be. So this first section of output, all these numbers, which I'm not going to make you look at, but all of the first step of output provides model fit information if you give the summary command in R with the fit measures equals true argument. And we're going to piece these, or go through these piece by piece to understand what each means. So these are the different sections that you'll see there, and we're going to start off with the unlabeled section at the top. So here, this unlabeled section is right at the top. It starts with number of observations itself. Stay with my slides as we do this, but all of this is in R. You can find it if you've tried running the model itself. So what we're looking at in this unstructured section is a global measure of model fit. And with that, we end up obtaining, let me just actually go back to the R code itself. So here, the missing number of observations and number of missing patterns should be number of observations should be pretty self-explanatory. Number of missing patterns talks about the ways that people are missing data themselves. In this case, there are 3. Because we have 2 variables, that means people who have missed did not provide data for usefulness, but provided it for performance. People who may have provided for performance, but not for usefulness, and people who may not have provided data for both. But generally, number of missing patterns isn't really that relevant to what we do. It just helps us understand how much of our data is being used overall. So the next section right here is really where we get our first instance of global model fit. This section, this block, is a likelihood ratio test. Remember, a likelihood ratio test compares a nested model with an alternative model. And in this case, the alternative model that we have is the saturated model, the one where we estimate all of the parameters, the 2 means, the 2 variances, and the covariance, or what we would call model 2 actually in our analysis prior to this. Now, the null model, the model nested within that, is our model specifically. And that's because our model has 4 parameters, 2 means, 2 variances, but no covariance. So a total of 4 parameters altogether. This minimum function test statistic here is what we call a scaled chi-square. I'll tell you more about why it's scaled and how it's a little bit different from the chi-square we may have seen up to this point in class in the next lecture. But for right now, just understand that this works as a chi-square. Here's the degrees of freedom for the test. This is the likelihood ratio test. This p-value right here indicates that the model, well, this p-value is very small. So now we have to think about what does that mean with respect to our analysis. Well, the p-value being low like that means we would reject a null hypothesis. And our null hypothesis actually happens to be that this model, the one that we're currently using, fits the data as well as the alternative model. This evidence right here with a low p-value suggests that really it doesn't fit as well as the alternative model, that perhaps the alternative model fits better. So what you end up getting along with this is right here, the scaling correction factor. That's the thing that turns this statistic into a number that we use for a chi-square. But we'll talk about that again in the next lecture. So generally speaking, this test that we see here, once again, if the test has a significant p-value, the current model, the one we currently have, is rejected. So we typically would say, hey, when we see this result, nope, the model doesn't fit the data. But it turns out, particularly driven by people who do work in structural equation modeling, that this test is usually ignored because it's said to be overly sensitive. Now, I happen to like the test. I don't think it's overly sensitive at all, but I think that that's just sort of the state of the art that we use in the social sciences. So you often see people not even look at that section of output. But what you want this test to look like is having a non-significant p-value, because then the current model, which is the null hypothesis, is not rejected. Otherwise, meaning that the current model seems to fit equivalently to the full model. So again, the saturated model itself comes from the model where we estimate all of the covariance parameters in our analysis. And so turns out Levon is actually estimating that model simultaneous to estimating our model when we go forward. Where the numbers for this output comes from actually is a lower section in the output. Where this 5.753 under the robust column shows up is from down below. Now I'll note, actually, before I get there, you'll note there are two columns to our output. Should have mentioned this ahead of time. The two columns right here, we have one that says ML and one that says robust. For our purposes, and pretty much every time you use analysis like this, in fact, I can't think of a case where you wouldn't, the robust column is where you want to be looking. I'll describe robust maximum likelihood in the next lecture, but for now just realize that this provides additional protection should our data not entirely fit the multivariate normal assumption that we're putting on it. So going back to our slides here, this robust column, so the 5.573, this line of output actually comes from the likelihoods that we saw in our data. So here, we knew before from previous classes that the likelihood ratio test is -2 times the difference in log likelihoods, and then that gets compared to a chi-square. Well, the ML column, the 6.064, is actually -2 times the difference in these two log likelihoods. And again, this log likelihood information comes from a little further down in the Levon output here. It's a little bit lower down. But -2 times the difference in these two numbers gives us 6.064. What the robust version does is it creates for each log likelihood what's called a scaling correction factor based on how closely aligned the likelihood is to multivariate normal, with a couple different specifics that I'll talk about next time. With those scaling reduction factors, it then goes and provides, it combines them to come up with the overall scaling correction factor, which is given by this formula right here, which you don't have to memorize because R will do it for us, thankfully. And sure enough, when we go and look at our model itself, the overall chi-square, 6.064, gets divided by this scaling correction factor. And so you see our number right here, 1.088, just reduces this just slightly and brings it down just a little bit. With this scaling correction factor, it should be equal to 1 for data that are multivariate normal, or right about multivariate normal when the assumption of multivariate normality gets met, and it goes above or below 1 based on various features of the data. So the other part about this that's nice is that if I were to go up and run Model 2, now remember Model 2 was our model where we had all of our parameters estimated. That model itself, you'll see, has 0 degrees of freedom in this section. And that's because it is the saturated model. We have 5 parameters in our model. There's 5 parameters in the saturated model. And sure enough, if you go and look at our log likelihood section, the log likelihoods are identical. But the part of this I'd really like to emphasize, though, is if you remember the ANOVA function where we compared models before in R, I can compare the model fit of Model 2 and Model 3 using this function. And the nice thing is it will give us that scaled likelihood ratio test automatically. This is something that M+ does not do. Right here is the 5.7529, which if we go back to our summary of Model 3's output right here, you'll see that value coming from ANOVA, 5729, is really this value under the test statistic itself. It's coming from the likelihood ratio test of the 2 models. So I think that's a nice little feature that R provides above M+ here. So our conclusion based on this test statistic is that this model fits significantly worse than the saturated model. Now again, that other part, where that first part of output, where this first section of output in R, this part right here comes from is this likelihood ratio section later on in the output itself. So if you see that the log likelihood H0 is equal to log likelihood H1, then you have perfect model fit. No other model fit is available. No other model fit is useful. You're basically fitting the same number of parameters as the saturated model. And I'll talk a little bit more about that at the end of the class. But again, where you can see this before comes from, this is the output from Model 2 fit, right, where we actually had 5 free parameters, which is the total number we can have in this analysis. And you'll see this is the values of our log likelihood. So oftentimes you may see that, and that's okay. That's actually preferable in some respects, because model fit then becomes not an issue. If you have perfect model fit, if you have a 0 degree of freedom test, there's nothing to worry about with model fit. You can move on to interpreting the data. This is something that reviewers often don't understand when they're looking at this, looking at the results. But it's something that you can understand from me here. But moving on, let's move on to the next section of model fit output, which is the model test baseline model. This is going to be a likelihood ratio test that compares the saturated model against a model called the independent variables model. This is testing whether any variables have non-zero covariances. So we go here. This is that next section of output in R right here, model test baseline model. Pardon me, go back to Model 3 output right here, model test baseline model. And you'll see the numbers that show up under the robust column are actually identical to the numbers that you see up in the likelihood ratio test. And that's because the Model 3 happens to be what's called the baseline model. The baseline model is a model where we've estimated each variable's mean and each variable's variance, but we estimate 0 of the covariances. Why this model is useful tends to happen in courses where, in analyses where latent variables are needed, because latent variables essentially are built off of covariances. And so this is a check to see if there's any covariances in your data at all that are non-zero. In this case, we would say, yep, sure enough, it looks like the one covariance that we have with this low p-value is significant. But generally, we don't often report this information. It's sort of information of last resort. If you really are trying to fool with the model, particularly in our models, the ones that we're going to do in this class where everything is observed, we rarely ever look at this information at all. So we move on to the next section. This is user model versus baseline model, and there are 2 different fit indices here. One called the comparative fit index, or CFI, and one called the Tucker-Lewis index, called the TLI. And what we want to see with both of these, now in our output we see a bunch of zeros here, which is a little bit odd, but that's just the way it works with this analysis of these 2 variables. These numbers, CFI ranges between 0 and 1, and TLI typically ranges between 0 and 1, but it can be actually bigger than 1. Where they come from is fitting a third model to the data, which is our independence model, and it's a comparison of chi-squares based on degrees of freedom with both of those. We don't need to really get into the specifics. But you'll want to know that these indices right here, what we're looking to see in model fit is that these indices are high or are close to 1. In fact, some prefer these to be above 0.95. I typically look at these robust versions that are right here. But right now we see that both of these values at 0 indicate that we still don't have good model fit, which is consistent with what we've actually seen up to this point. So, moving along. The next section of output happens to be information criteria. This information criteria we already talked about log likelihood, but we didn't talk about this last section of the log likelihood information criteria. So here, this tells us the number of parameters in our model. This is a good place to check to see that we're running the model we think we are. This model 3 had 2 means, 2 covariance, and 2 covariances, or 4 parameters. And sure enough, it lists 4 parameters right here, so that's a good sign. Then the 3 numbers that you see below this, AIC, BIC, and sample size adjusted BIC, these numbers are used for model comparison of non-nested models. So what do I mean by that? Let's imagine you fit 2 models. You're not sure whether model 1 and model 2 are nested or not. You want to know which model fits better. For each of these statistics, let's take AIC as a first step. AIC then should be compared with the AIC of the other model, and the model with the lowest AIC is said to be preferred. Now you'll note there are 3 different indices, so it's possible, and actually probable in experience, that maybe 1 or 2 of these indices prefer one of the models, whereas another index might give you discrepant or divergent information, and that is entirely possible with how it works. So I like to say don't use these, don't ever use these when it comes to nested models. Stick with this likelihood ratio test for nested models. If you have non-nested models, and in most cases you can structure analyses in ways that you can always use nested models for the most part. But if you have non-nested models, then that's the only time you look at this section. We don't have non-nested models, so this section doesn't matter to us. Okay, that was the precursor slide to the last one. I have some repeated slides in here. The next to last section of model fit is the root mean square error of approximation. That is this section right here. RMSA is what it's called. The number we're interested in is this robust RMSA. I like this one right here. This is a confidence interval for a 90% confidence interval telling you the range of it in which it may fall. What we want this number to be is low. And so this is kind of the opposite of the values that you saw up here with the indices. We want CFI and TLI to be high. We want RMSEA to be low. The way I like to think about it, memorizing these numbers where we want them high or low, is that R stands for root, and roots from a tree are typically on the ground or are low. So we want anything that starts with a root or having a root in the name to be low, whereas we want anything that's an index to be high. So with respect to the root mean square error of approximation, it comes from how far off this model is per degree of freedom for the chi-square. And so it develops this using formulas that you can see up here. And what we want this to be is less than or equal to 0.05, although you'll see that there are many other people publishing RMSEAs in different ranges. You might actually see RMSEAs in this range. There's a well-known scale that people use called the BASC, and in their technical manual, the RMSEA reported is like 0.18 or something like that. So RMSEA, I'm pretty strict about it. I like it as smaller than 0.05 because the closer we get to the model fit, the better we can trust our results. So we look at our model. Our model's RMSEA is 0.12. Again, this tells us, yeah, this model doesn't fit the data very well. So there we go. Next and last is the standardized root mean squared residual. So all these things pretty much sound the same, whereas the RMSEA was based on kind of chi-square statistics and a likelihood ratio test. The standardized root mean squared residual looks at the correlation matrix that our model implies about the data and compares that with what's observed in the data set itself. So here, this is on effectively the scale of correlations. It says we're on average off by about 0.06. And overall, we want lower to be better. Some like this better than 0.08. I've never found an honest standard to say why that's the case. Why less than 0.08 doesn't really make a difference. So when looking at all these statistics, the way I like to think of model fit is sort of building a portfolio of evidence for it. If we go through these again, we can go from the top and say, okay, the likelihood ratio test of 5.573, this thing says the Model 3 does not fit the data well. Okay. We don't care about the model test baseline model. That one doesn't matter to us. But the CFI and TLI right here, these both should be above 0.95. They're at 0. This also tells us our model does not fit the data well. Moving down, we don't really get any model fit from the information criteria section that's used to really form the likelihood ratio test. And we don't need these because we're not comparing models right now. But we get into root mean square error of approximation. We see it's 0.12, and yet again, this tells us it doesn't fit the data too well. And finally, our standardized root mean squared residual, 0.066, this tells us yet again that doesn't fit the data well. So our pieces of information here, 1, 2, 3, 4, and 5, all of them are negative about this model. All are saying the model doesn't fit the data well. So in that regard, we would probably conclude very quickly that this model does not fit the data as a whole. So the next question then arises is, how on earth do we make the model fit better? What do we do when a model doesn't fit data? Well, one thing that we can typically do is pull from the data, from the analysis itself, something called local measures of model fit or model misfit. These local measures point or give us kind of specific information as to where a model may not fit very well. All right, so these are opposed to the global measures that just give us an overall thumbs up, thumbs down, yes, no, it doesn't fit with the model. What these measures are trying to do is provide us some indication of where our model is off. If our model is off for a given, between certain covariances, for instance, is really what we're to look at. Or we may also be able to get the other types of localized model fit information through something called modification indices. These modification indices are awesome. They're awesome and voodoo at the same time. They're 1 degree of freedom tests. And what they do is they're actually something called a score test. So if you're into statistics, the likelihood ratio test has an asymptotic equivalent, something called the score test. Basically, you fit a null model, and the score test tells you if the parameters that were not in the model should be added. Well, this tells us for every parameter that could be added to the model, whether or not the model improvement would be significant. So should we add that parameter to the model itself? So let's go into both of these a little bit more here. The residual covariance matrices you can produce through the commands that you see on the screen here. Residuals model03.fit type equals normalize. So actually I can put this down right here. Normalized residual covariances are nice because they're on the scale of z-scores. And so what we see here in our normalized residual is this covariance and this mean section. What does this refer to? Well, it turns out the mean represents the mean vector, and the residual here represents the difference or the normalized difference between what our model thinks the mean vector should be and what the data thinks the mean vector happens to be in the saturated model, in this case the data. So you can see these values are negative, but they're also very small. And so really what happens when we look at this is the values that we see only become cause for alarm if they become bigger or smaller than something like a z-score would be, something like a 2 or bigger, or something like a -2 or smaller. So both of the mean vector values are not big. They're very small, and that's because our mean vector in our model is saturated. So we don't have a place. This tells us, when we see small values here, it says don't change anything about this variable. So we're not going to change anything with respect to the means for performance and usefulness. Now, comparatively, if we go into the covariance matrix, what we see under the normalized residual is, again, our model's implied covariance matrix, which I'll remind you has a 0 value for the covariance. We compare that with the saturated model's covariance matrix, and that's where the covariance was estimated. So what you see down this diagonal is sort of the normalized difference between our model's variance for performance that's highlighted and the saturated model's variance for performance. And so performance, that variance has a very small normalized residual, so nothing's wrong with the variance. Same thing with usefulness. There's very small normalized residual. But now we look in the off diagonal, and this is the covariance between performance and usefulness. And sure enough, there's a value bigger than 2. What this is telling us is that there is a big discrepancy in the estimate, our model's version of the covariance between these two variables versus what the data think that covariance should be. So if we were to go and revise our model, we might consider adding the covariance between performance and usefulness. Well, sure enough, in our model, that covariance was set to 0. So we know that that's going to be a problem. But this is the way that we discover it's a problem, through this normalized residuals of model fit. The next place that we can look at are these awesome modification indices. To get them to display, you can type mod indices as a function. Give it the model03.fit, and out will come every parameter that's not estimated. And it gives us values in this table. So let's describe what this means. This says, for our model, the parameter that looks like in Lavon's syntax, perf double tilde use. What is that in syntax? Anytime that you see a variable with a double tilde in between another variable, that refers to a covariance. So this says, if you were to estimate a model with this covariance being estimated, you would expect the chi-square to be somewhere around 6.239, or in this case, MI scaled, this is our scaled chi-square, to be about 5.7. Well, we know what that happens to be because we've actually observed this in our model. Right? When we compare our model 3 with model 2, or the saturated model, we saw that the chi-square is actually about 5.57. So yes, this modification index is trying to tell us, hey, if you want to improve the model fit, here's one way you can add one parameter and get a significant difference, and that's by adding the covariance between the two values. So the modification index, the scaled column, is where I tend to look. What you're doing is this value right here is the chi-square. Oops, that 5.734 is a chi-square. So with 1 degree of freedom, a chi-square to be significant needs to be, or the 0.05 level needs to be bigger than 3.84. Now, if you have a very big model, every time you look at a modification index, that's like doing a hypothesis test. And so it's very quickly that you can get into a case where you're adding parameters that may not need to be there. So in practice, lots of people like to advise saying, make this value as big as possible, or maybe 10 or more, or something like that. So that's the column that I look at, MI scaled. The other part you should look at is EPC, which stands for expected change in parameter, which tells us that the model thinks that the covariance, if we were to add this value to the model, it would be about 7.125. So to recap up to this point, what we've learned from the absolute fit indices is the model did not fit overall. What we learned from the localized fit index is the reason the model is not fitting is because the covariance between performance and usefulness has not been added, and it needs to be there. So the next step in this analysis would be to add that covariance to the model and rerun it. And that would give us actually model 2. But the other thing I want to do is to compare the differences in these values when we look at model 2 and model here. So let's go back and look at our overall model 2 value here. You'll note the model 2. I pulled this up in the lecture earlier, but we saw when we just run model 2, we saw 0 degrees of freedom. We saw that there were 5 parameters that we were estimating. Well, it turns out when we see 0 degrees of freedom in this very first spot, nothing else matters because all the other values indicate perfect model fit. And sure enough, everything's perfect because this is the saturated model. So when you see a 0 here, that's great. That's good news. So model 2 is saturated. But what about univariate models? if you go to the very top of this syntax, you'll remember we started this lecture, or the introductory lecture, by fitting a univariate model for performance, right? And when we do that, we had an empty model where we took there's the mean estimate or the intercept of performance. Here's the variance of performance. But let's take a look at the model fit for that univariate model. Sure enough, there are 0 degrees of freedom. And that's because in model 1, there is one mean and one variance, and we estimated those 2 parameters. So every univariate model that you run will end up having a 0 degrees of freedom to it. And that's because, every univariate model that you run where you estimate the residual variance, if you don't fix it. I guess in theory you could fix it, but that would be a very bad idea. But in every univariate model you have run where you've estimated the residual variance, it's been saturated. So we never ever had to consider model fit in univariate models because the model was always saturated. Okay, well that wraps up this getting into model fit. So what we found here was model fit's the biggest difference between univariate and multivariate models, and univariate models are saturated models that fit perfectly always, so long as we estimate the residual variance. We also learned that global model fit helps us determine the overall absolute model, yes, whether or not a model fits the data or not. Those are indices like RMSA, the likelihood ratio test with the saturated model, the CFI, the TLI, and the standardized root mean squared residual. When we see our model fits poorly, we end up going to our local model fit to see which parameters we could use and we could add, and we can figure out whether or not we need them. So that is absolute model fit. But what about the case where you have 2 models that fit the data well absolutely? How would you want to compare those 2 models to see whether or not one or more fit the data, or whether or not which one would be preferred to each other? Well, that comes up in the next lecture. So that's all for now. Thank you for watching.